Okay, we're still in 10.5 of Barnett, and we're going to look at some applications next. So remember, the derivative gives us what we call the instantaneous rate of change in 10.4, okay, of our function with respect to x. So what could that be? Well, that could be instantaneous velocity if our function is the position function, right? Then the derivative is instantaneous velocity. It could be the tangent line slope at a point on the curve of the function, or it could be marginal cost, which is an econ topic we'll focus on next. If c of x is the cost function, that is the total cost of producing x items, then c prime of x approximates the cost of producing one more item at the production level of x items. Read that one more time. C prime of x, the derivative of the cost function, c, approximates the cost of producing the next item, or one more item, at a production level of x items. So if you're producing 10 items, and you know what the cost of that is, c prime of 10, the derivative at 10, will approximate the cost of producing the 11th item, okay, at a production level of 10 items. Keep that in mind. So c prime is called the marginal cost, and we'll look at some examples of that. For our starters, let's take a look at this example. This is a tangent line example, and we're going to have our function f equal the polynomial x to the fourth minus 6x squared plus 10. How do we find the derivative f prime? Well, we use the rules we just learned in this section, and that's going to be, according to the power rule, 4x to the power of 3 minus 12x, and that's that. And then they want us to find the equation of the tangent line at x equals to 1. Well, we know that we're looking for an equation of a tangent line. Well, the slope of that line, slope of our tangent line, is the same as the derivative at x equal to 1. So all we have to do is find f prime of 1, right, by plugging in 1 into this formula. We could do that. And the derivative at 1 is going to give us the slope of the tangent line at 1. So we know that the slope is y equals negative 8x plus b, right? So the line looks something like this. To figure out what the rest of the formula is, what is the b in other words, we need the point of tangency. That's the point where the tangent line and the function touch. Well, notice we're looking at x equal to 1. When I plug in 1 into my original function, I get f of 1 equal 1 to the fourth minus 6 times 1 squared plus 10, where I get 1 minus 6 plus 10. That's negative 5 plus 10, or 5. So I know that the point 1 comma 5 lies on my curve and on my tangent line. Okay, that's called the point of tangency, 1 comma 5. So I can plug that in for y and x here. I could have also used point slope form, by the way. I'm just sticking to slope intercept. And that would give me 5 equals negative 8 plus b, or b is equal to 13. So the equation of the tangent line is y equals negative 8x plus 13. Okay, that's one way to find it. Another way you could have gone for it is used, like I said, point slope form. Once again, knowing that at 1 we're at 5 on our function, we could have just used point slope form as done on this slide, plugged in 5 and 1 for y1 and x1 respectively, and gotten the same equation, negative 8x plus 13. That's what we obtained as well. Okay, here's another application example. The total cost of producing x portable radios per day is given by this function, c of x, where x is between 0 and 100. It says find the marginal cost at a production level of x radios. Well, once again, the marginal cost is simply c prime of x. So to find the marginal cost, I need to take the derivative of this expression. And the derivative of the constant here is going to be 0. The derivative of 100x is going to be 100. And the derivative of negative 0.5x squared is going to be negative 0.5 times 2x, or just 100 minus 1x. So there is my marginal cost, 100 minus x. Okay, that's the answer that we're looking for. Part 2 says find the marginal cost at a production level of 80 radios and interpret the result. So we want the marginal cost, c prime of x, at a production level of 80 radios, means x is equal to 80, and interpret that result. So what are we looking for? We're looking for c prime of 80. And since we found c prime of x to be 100 minus x, c prime of 80 is simply going to be 100 minus 80, or 20. And again, how do we interpret that marginal cost? Do you remember the magic sentence? What that means is that it will cost approximately $20 to produce the 81st radio, right? So if you produced 80 already, it's going to cost you about 20. By finding out C prime of 80, you're finding approximately how many dollars it's going to cost you to produce the 81st radio. Well, you might be wondering, but I could actually find out the exact amount it will take me to produce the 81st radio. And in fact, that's what they're going to ask us to do in part 3. How do you find the actual cost of producing the 81st radio? Well, wouldn't you agree with me that if you find how much it costs you to produce 81 radios, and from that subtract how much it costs you to produce 80 radios, then you have found the cost of producing the 81st radio? So if you find this difference, C81 minus C80, then you are really finding the cost of producing the 81st radio. That calculation finds the exact or actual cost. Okay, actual cost. Remember, using the derivative is an approximation, like we did in part 2. That's why they want us to compare the two answers. Let's see the math. When you do the actual cost of the 81st radio, it will be C of 81 minus C of 80. So you got to go back into your original formula for C of X to plug in 81 and 80, respectively, and you get $19.50. So that's very close. C of 81 minus C of 80 is approximately very close to C prime of 80, right? Which is the derivative at 80, which was $20. So we got $20 one time, and using the actual formula, we got $19.50. So you could see why the derivative is helpful here. It's a very good way to approximate how your cost will change by producing one extra item, the next item, the 81st radio in this case. That's where it's used in marginal analysis. Okay, so here's a nice summary of this section. So we learned some key rules. The derivative of a constant is 0. We learned the power rule, which says the derivative of a power function x to the n is n times x to the n minus 1. We have a constant multiple of a function, which says the derivative of that is the constant times the derivative of the function. The sum difference rules, which tells you that the derivative of a sum is the sum of the derivatives, and the difference of the sum is the difference of the two derivatives is the excuse me, I mean to say the derivative of a difference is the difference of the derivatives.